night. It's probably hard. It's probably hard for people to meet on Friday night.
Sure. Yeah. I think we can we can be adjust, right? What day that we can't do Burin, that is there any incident? Oh, we mentioned about in January, right? But we need to get
Yeah,
confirmation first, right? Yeah.
right.
How
Yes.
about on next Wednesday? We have anything on next Wednesday?
Yeah, I think we have. Let me check.
No, we don't. Well, next week we're scheduled for. We're meeting on your Monday night
Mhm.
for sure. We're meeting
Yeah,
on
we have
December
Monday, Wednesday.
Thursday, and
Mm.
Friday. Yeah, see, it's a little
Yeah.
bit.
And are you going to, like the father of our center director just passed. And the center is the host for the funeral on Wednesday. Do you plan to go too?
Yeah, because we had the meeting, so I might
Mm,
have to go maybe this weekend instead.
mm,
Because
mm,
otherwise I cannot come back in in time to set up the meeting.
Uh-huh. Yeah. So you plan to switch, right, to go during
Yeah, I
the.
think so.
Okay. Yeah, sure. And then I will, you will stand by mm, and help run this.
Yeah.
Okay.
Well, should we start?
Yeah,
Yeah, please.
please.
Okay, I think everybody can see my screen. Is that correct?
Yes, we can.
Yes.
So what I was hoping we would do today is really solidify. So when I last met with you, the goal was to introduce you first to explanation and then to modeling, because writing explanations and writing modeling and constructing models are really important to many of the curricula that you will be all the curricula that you will be experienced, the water quality, the health in our hands, and the interactions. But it's also a very important practice in science education. So you could, hopefully you'll use the explanations that are in the curriculum because they're embedded in, as you saw working with Anne yesterday. But it's very important also for your practices in general, right? So helping your teachers understand explanations in general and understanding modeling in general is really important. You really want to try to use those in your throughout your instruction in science, because it's really when kids construct things, it's really what helps them form really deep understanding. So my hope today is to really continue to build this common understanding of how to support students in building and revising models and scientific explanations so that you have a really strong understanding of how to do it. And of course, I'll try to, hopefully we'll have a lot of good discussion. There's not that many of us, so I can respond to lots of questions that you have, because when you leave, I'll still be with you for the next couple of, month or two. But after today, I hope you all have a very strong foundation of what it means to construct a model and to write scientific explanations. And of course, I'll have us construct some models and construct some explanations. And I like to think of that as engaging in doing science. I'm going to, and again, I'll respond to any questions you have throughout the day. So that's what I hope to get accomplished today. I did, I was asked actually if I had some high school examples of explanations. The only ones I could find actually are in interactions. And so I thought rather than bring them up now, I will just deal with them in interactions. I couldn't really find any that I wanted to share in the high school physics and chemistry. I really didn't have enough time to dig around. So I'll have to go back and look. but I just wanted to respond because I said I was going to look for that, but I did look, but I couldn't find. So that's what we hope to accomplish today. I don't know if anybody else has anything they want to contribute and what they want to get accomplished. Okay, so we're going to begin by reviewing, we're going to jump back into building models. So I'm hoping to spend this first hour on reviewing and building models, a review of building models. And then we'll jump into explanation. So remember, all models always start with a question about a phenomena. And what you're trying to basically come up with why does this occur, right? So all models try to present some form of a causal explanation. So we really want to think of models as tools that actually allow us to explain the mechanisms that happen in phenomena. And because they do that, they actually allow us to predict future events. Models also facilitate communications. If we're trying to show people why does this thing happen, models, because of their visual representations, actually become very powerful in that aspect. And I want to stress that all models have limitations. Models are not replicas of the world. Models explain. And because they explain in the best way we possibly know, they all have limitations. The classic example is thinking of the Bohr atom. The Bohr atom is actually a powerful model from one day, having electrons that exist as point particles that spin around the atoms. That's a powerful model, but it has its limitations in really trying to explain all phenomena. It can't explain all phenomena. And of course, that's why we went to more sophisticated ideas of what do electrons around atoms look like. And so we have, electron cloud theory. And so we move from one model to another model, primarily because models have limitations and can't explain all the phenomena. It doesn't make them one model more right or more wrong. What it makes the models aren't neither right or wrong. Models have to explain, and we use the models that best explain as the current scientific thought. It doesn't mean the other ones aren't useful. They just aren't as powerful. So I like to think of the value of models in their ability to be able to actually explain phenomena. And of course, current scientific thought always uses the most powerful, but it doesn't mean the other ones are wrong. It just means they have some limitations. All models have limitations and probably will be replaced by other models. So what you have in front of you, I hope, is a chart that summarizes many of the important aspects of what modeling is. So you'll see on the left-hand corner is this aspect called essential aspects of modeling. And of course, the first one is that it explanations and predicts. The second column, we go to what a student should be able to do when using models. In here, it's the ability actually to generate an explanation or make a prediction using a model, right? So you have both create a model, generate an explanation, but you also have use a model with respect to predict. And then the last column, we have how will students demonstrate proficiency. And so students, and by proficiency, I mean their knowledge of actually being able to use that model. We have students use a model to correctly explain or predict a real world phenomena. So that's one important aspect of what modeling is all about. Now, with respect to constructing models, we really want kids to be able to identify the parts of the model. In here, it's the ability of the student to be able to identify the parts, i.e. the elements and the variables of a model. And what we look for, does the student correctly identify all the appropriate and necessary parts that really are essential in the model and not put extra stuff in. The third essential aspect is that they can actually make the relationships among the model parts. And this is where kids particularly show how one part of the model relates to the other part of the model to actually allow it to occur. So that that's the third aspect. And of course, what we would expect for students to demonstrate proficiency is that we actually see the student be able to correctly describe the appropriate relationships and interactions among the parts of the model. And the next important aspect is this notion between the relationships between the model and the real world phenomena. Do the parts and the relationships that the student made or the scientist made actually correspond to some real world aspect and the ability to be able to explain it? So here it's the students correctly describes the relationships between the model and the real world phenomena by showing how the various parts, the relationships really work together to be able to predict and explain the world. And of course, the last part then is limitations, as I talked about. All models have limitations, and you want students to be able to identify what those limitations are. That's a more advanced feature of modeling, but it's an important aspect of modeling. So that's a big summary of various aspects of modeling, and I hope you recognize that we covered some of these the last time. And I'm just curious, before I move on, if you have any questions with respect to this chart, because we're gonna hopefully this will be a foundation for you in looking at and helping others understand what modeling is. So are there any questions or comments? You can either say it out loud, raise your hand, or put it in the chat.
I have questions, please.
Okay.
I still have difficulties in distinguish between some words. Modeling, explanation, and argument. To me, it's all connected, and I cannot distinguish them.
Yeah, that's correct. So they are in the scientific world, they are very connected. And so one way to distinguish a model from a scientific explanation is think of a model as a representation, right? Like a drawing, a picture. Now, all models don't have to have that, but an essential feature of modeling is that it's not just words. It's drawn as a representation. That representation typically has words associated with it, but it's the key factor in the model is that there's a representation. Now, as you get to understand modeling better, you'll also realize that models can also be equations, right? So for instance, F equals ma, right? Force equals mass times acceleration. That's a model. That's telling us that when, if we're going to understand the force of something, we have to know the mass and we have to know the acceleration. And if we know the mass and acceleration, we know what the force would be on an object if it got hit, right? So that's a model, but that's a mathematical model. So models can be, so to understand modeling, you want to think of it as some other representation rather than a text description. That's a model. When we go to an explanation, you want to think of an explanation as as basically something written in words. Now it could be exactly the same thing as F equals ma, just like what I said to you, right? Because I said, look, if we want to understand force, then we have to consider mass and an acceleration and how fast something is accelerating and how heavy it is will really impact the force. That's that's an explanation. And it's related to the model F equals MA, right? So they're very, very related. Essential to any explanation is always having your evidence and the reasoning behind it. Now, the difference between, so you make a claim, that force is equal to mass times acceleration. That's the claim, right? That's it's the model. And I have a lot of evidence and reasoning behind that, right? Because how heavy something is and how fast it's, not how fast, but how it's speeding up, right? Because that's what acceleration is, will really predict the force. But an explanation, there isn't any kind of debate. No one's going to debate that the faster something's moving or speeding up, and the more mass it has, it's going to have a greater acceleration, a greater force. No one's going to debate that. That's an explanation. You get an argument when when it's not as clear from one point to another point, right? So and there's a variety of different alternative explanations that you really can't rule out. So if you can't rule them out, then you have an argument and you're trying to find out which one has more and more evidence to support your case. So arguments are very related to explanations, but often sometimes there isn't a debate. And so when there isn't a debate, there really isn't there's no argument involved.
Okay, that's much clearer. Thank you so much.
Yeah. There's also a question in here related to modeling. What type of model should be? Concrete, drawing, formula, equation, relation, visual. So in our work, because it's middle school and high school, we actually focus a lot on representations. So drawings. In some of my more advanced high school work, we do go into formula and equations, but we won't be doing that either in water quality or health in our hands or interactions. So you can think of modeling as what that's in the chat in all those ways, except we won't be dealing much with the formula and equation aspects. So they are, to go back to the original question, they all are very tied together. And often when you're trying to create an explanation, you might provide a model that goes along with it, because that's really going to support your explanation. And if you look at the world of science does, of course, we're in instruction, and we're trying to help kids understand these various parts. And so we try to simplify. In some respects, we try to simplify it for them. So we're saying, here's an explanation, here's a model, here's an argument. So you can almost think of that as a scaffold, right? Instruction, we can't tell everybody everything at once, otherwise they're not going to learn it. So we try to break it down into smaller parts. And hopefully, because they're working with ideas in middle school, in beginning high school, by the time they become seniors, they have a much better sense of how these various aspects work together, how these various features of what it means to do science actually work together.
So I have a question.
Okay.
Yeah. For the first row, explanation and prediction, it seems that students demonstrate the same things with the row, the 4 row, relationship between model and real world phenomena. So the explanation, they have to predict and also explain the real world phenomena, but in the 4 row, when they relate between model and also real world phenomena. I think it's the same with the explanation or prediction.
Time out, time out, time out, time out, time out. So for some reason, I don't know if anybody else is, but I got terrible feedback. So did any of you?
Station, I think, or
Yeah.
airport.
So I don't know what that was. I couldn't understand you.
I'm sorry, I am in the station now. So
Uh,
I will write down my question in the chat.
So I can't understand. If you want to type it in the chat, I can try to respond it that way, but I could not understand you. I just
Yeah,
couldn't
she
hear.
said she will write it in the chat.
So that is another question from Dr. Pachali. Right.
There's another question.
Yeah, before Dr. Murray about the model.
Oh, yeah.
I think that Professor Joe is already responded to my question ค่ะอาจารย์ตอบไปแล้วค่ะ
Okay, ตอบแล้วนะ
ค่ะ
คะ
ค่ะ
I did. Thank you.
May I ask the question? So it's capability, like how they will do the modeling and how they will show their proficiency while they would do modeling and so on. But I have a question. So regarding the essential aspects of the modeling, and there are the limitation and real world phenomenon. So to which grade or what kind of school is more, I mean, will the level of the modeling go dig deeper and go down with these essential aspects of the model? Let's say like in a senior school, they will have the like a explanation, prediction, and do some parts of the modeling. And in high school, they will more do the relationship between model and real world phenomena and solve something big problem and do the more challenging model, create the challenging model.
Right. So a lot of it focuses on so for instance, the model that Anne started to show you yesterday. Well, she didn't show you a model. Often what happens in more in the middle school, you're a little bit more at the descriptive level, at the macro level. So instead of showing what's happening at the invisible level, right, you're more focused on the larger level. So you could say, for instance, and this is a model, right? You could say that water quality, or that the amount of my pH impacts the amount of my water quality. So that here, I'll show you. I'm going to stop sharing, and I'm going to pick up a whiteboard. And I think I figured out how to do this. Last time I forgot to say new. Okay, my tools disappeared again. Why do my tools? Why did they disappear? Well, I had them last night again. Can't believe this.
Okay, Joe.
Okay.
Let me try this. I will start the whiteboard and then you can write on it. Okay, can you stop?
Okay,
this
I'm going to stop. Yep.
Okay, let me share the whiteboard now, and then I think everyone can write. Okay, can you try?
Yeah, I don't have any go parents. I really don't have any tools. It's quite amazing.
No, really?
So even
Because there's
when you
someone
just
writing
shared, I don't.
something.
Oh, yeah, yeah, but I don't have them. And there's no way I can find. Let me go to my whiteboards. That's just amazing.
Yeah, Darren can draw.
Well, I'm glad someone loves it, so that's good. Yeah, I can't, that's, okay, let's stop this. We don't, I'll just talk. Wow, I, I even double checked last night again. Okay. So you could take like, I'll just show with my hands. You can say you have something like pH, right? Can go to impact water quality. So that would be a model. I picked an element, pH, and I pick another one, water quality, and they affect each other. So that is a very simple descriptive model. As we get older, we really want to have kids construct more mechanistic models where they really go down deeper. So there was we got the comment in the chat rather than speaking it. She was able to write it. So it says, it seems to me that when students perform an explanation prediction, they connect their explanation with the real world phenomena. I think it is the same when they relate the model with the real problem. So what actually is the difference between these two? So once again, I'll stress this. A model is more of a representation or you draw something rather than, or a formula rather than just purely a descriptive explanation. Now, in the US, that distinction, and you'll have to specify, you'll have to see if this is true for your own countries, because I really don't know this one for your countries. In the US, when children draw models, it's really valuable for kids who aren't very verbal. I think you all know there are some children who are very good at writing, they're very good at speaking. So when we ask them to write a scientific explanation, that really favors them. And there are some other kids who might have the knowledge in their head, but because English isn't their primary language, or because they're just not as fluent because of their background, they can't express it as clearly. But interesting enough, they can draw it. So when so drawing becomes another representation of how to get kids who aren't as verbal to actually show their knowledge. That's one of the other primary reasons why I love modeling, because it allows in the United States, we have, and this population is growing bigger in the United States. We have lots of second language learners. We have a lot of people from Hispanic backgrounds, and we have lots of people from various Asian backgrounds in which English is not their first language. And so it's hard for them initially to, they're not going to write as fluently as some other people. So modeling, because it's another form of, another form, it's like a drawing, they can actually represent their knowledge much better. So there are these very overlapping similarities as was expressed, but they're also they also have their very distinct features. The other reasons why I really like modeling is because it goes back to some of the initial ideas I started talking to you about. And that is, I really want kids to form deep, usable understanding. And when students not only express stuff, in schools, the primary way of expressing ourselves is through language, text. But that's only one pathway in our brain. When we can get children, we can get learners both to express their ideas in language, in drawings, in other kind of movement, right? Like they could act it out. If they could build a model can also be a three-dimensional thing that they actually build. Those are different ways in which students can really encode, really form deeper knowledge. So for those of you who are interested in this, it's called dual coding theory, and it's by this wonderful scholar called Pavio, who really stresses that if we really want to, has good evidence, again, he provided an explanation, it could be an argument in this case, that when learners can express themselves in more than one way, right? In text, in a drawing, in acting something out, and building something. This is where they really form really deep understandings, because in their own minds, they've actually encoded things in a variety of different ways. So that's the other reason I really like modeling. And there's a couple of really interesting comments in the quote. So Sherry writes, and I really like this. This is really a nice one. Where's Sherry at? Anyways, I really like this comment. That's really nice, Sherry. She writes, a model is like a voice for quiet ones, to introvert students. And that's really true, right? And some kids just like to draw, and can, even when I say kid, I don't necessarily mean an elementary student. It could be a high school student as well. When children can draw something, right, it really gets them to express themselves. So I really like that comment, the very nice comment. And the other comment below here is, a model is like a way to communicate with others, to show their understanding and explanation. That's absolutely really important. One of the major functions of a drawn model, of a three-dimensional model, is really to communicate. And so that's also a very important comment, so that I find very valuable. So Agama, you're going to have to say to me, I don't know what you mean when you say the scheme. What's the scheme?
Maybe I misspelled that. I mean, sometimes, like in biology, sometimes we do use the scheme to we're drawing some different shape of, not the circle as we did last time, but another type of the like a figures to explain ourselves, to like subdivide something, you know. Is this some other type of the modeling, or is this something different? I just want to make clear for myself. So let's say when we give the information, we subdividing, drawing the lines or drawing the circles and showing the differences, and using kind of do the modeling as we did last time. So yeah, we do the branches. So is this the same?
So think of, since you're a biologist, right? Think of DNA, right? So we draw DNA, and we draw the backbone, and then we draw a helix, right? But those images of DNA, are they really DNA?
It's kind of just information.
It's just information, right? It's trying to represent to us what DNA looks like. It's not really what DNA looks like, right? Often it tries to represent the hydrogen bonds between the sugar molecules, right, that holds it together. It shows it with little dotted lines. Is that what a hydrogen bond is? Absolutely not. It's a way of representing that these things are being held together by these somewhat strong forces, but not really a full bond, right? So in that respect, that's a model. So those drawings that you see in biology are also models, because they try to explain to us what a model, what the thing is. I'll give you another example, and then I want to just go on to one or other. I just want us to get us to draw one last model. So often, teachers will have kids put in, at least in the United States. I don't know if you do this over in Asia, but anyways, they'll have kids take a variety of different vegetables. So they might, for instance, say a pea pod is a mitochondria. And then they'll take something else like a radish, and they'll say, oh, that's the nucleus. And then they'll take some other kind of vegetables, and they'll put it in a bag, and they'll say, that's another part of the cell. That's not a model, because it's not explaining anything. But when we draw pictures of how parts of the cell interact with other parts of the cell, that is a model, right? You always want to make sure that what you're doing every picture, every drawing is not a model. You have to make sure that it's actually explaining something related to some question. So
I
as
see,
soon as I say, how is one part related to another part, and I show you that in a diagram, like if I say, how do the strands of DNA actually stick together? And I draw this double helix and I show you how the hydrogen bonds are holding it together, that becomes a model. If there's just a picture of a DNA and it says, this is the way DNA looks, it's not necessarily a model because it's not explaining anything. You want to make sure that models are always explaining something, and that can
Okay.
allow you to predict, right? That's the critical aspect.
I see.
Joe,
Practice
maybe,
make clear.
Joe, maybe I ask last one, like the model for that kids construct to solve the problem also called a model.
I'm sorry, say it again, Kesra.
Like what I show on the screen here, like when
Ah.
kids try to solve some problem and they create the model, right, to solve problems.
Right. So stream tables, right? So this coast, if you're building like these in the United States, we call these stream tables, and you're trying to show how to prevent erosion.
Yeah.
Right. That's what I think these things are doing, right? Is it's trying
Yeah.
to prevent. Yeah. So right. So for instance, you see in this middle one here, can everybody see my cursor? Wait. You see in this middle one right here, that's got these blue things and it's got these rocks.
Yeah.
And then it's got some sand, right? I
Yeah.
think what this is trying to show that these rocks are holding back the erosion. So as long as it's doing that, it's showing something about how to prevent erosion, then it's a model. And I think stream tables, where kids are actually, building these things and then flowing water through them to show how the movement of the water really affects the erosion. Those are wonderful examples of models because they're really trying to explain and demonstrate the impact of the flow of water. And one of the reasons I really love them is when you build a very simple stream table, you see some of the real features that actually exist when water runs on land, right? So you see how this you can see the curving of the river and how it erodes away the banks of the shore. And if you have harder materials, how it's much harder to erode that material than it is to erode soft material. So I really find those wonderful models that kids can use to really build up their understanding, to understand erosion and how to prevent erosion.
Thank you. I stop share. Yeah.
Okay, so I think what we're going to do is I'm going to share my screen again. So yeah. So remember, these were our steps in building a model. And remember, just like with Kethra just showed us, you're always answering a question. Why does erosion occur? How can I prevent erosion? So you're always, every model always responds to a question. So in this particular case, you always have to plan your model. The first step in planning is what's inside my model. So you have your various, you can call them elements, factors, or variables, depending on what grade level you are. Then you want to show the relationships that exist. Second step is showing the relationships that exist between those various elements or factors or variables. The third one is to really test it by saying, does this really account for it? One of the reasons why I love the stream table examples is you can really put water on them and really see, does it prevent the erosion? Do those bricks, those rocks really hold back the erosion that can affect the shore? So that's why I really love when kids build stream tables. And then, of course, the last one is to revise your model to make sure to make it even work better. So those are all the various steps in building a model. And I just say that in review, because what we're going to do right now is we're actually going to build a model. And so I'm going to show you a phenomena. I think many of you have seen this sometime in your life. These are just this is just a jar. And in the jar is just hanging from a piece of metal, right? This is like a paper clip. And this is simply an aluminum ball. And these are just two pieces of really thin pieces of metal. And I'm going to show you a video of this. Now I have to stop I'm going to stop sharing and I'm going to reshare because of the way this is set up today. Everybody can see that, right? Yeah. So when I bring a charged rod, right? So if I take a rod, like a plastic rod, and I rub it with wool, it becomes charged. And if I bring it close to those pieces of gold foil, what happens? So I'm going to play it. Hopefully everybody can see that. And you'll notice that as I brought my rod close, I'll do it again. As I brought my rod close, the leaves spread apart. And of course, then when I take it away, it falls back down. So I'm going to do it again. Really kind of an interesting phenomena. So your charge, everybody saw that, right? Everybody know the phenomena? Everybody's seen that phenomena. Okay, so I'm going to stop sharing. Questions in the chat. So I'm going to stop sharing and I'm going to now share again. Okay, so here's your task. We're going to hopefully go into just a few breakout rooms. I think maybe we can go into 3 breakout rooms today. And I want you to develop a model to explain what causes those little leaves, those pieces of foil, to move apart when the charge rod touches the metal ball. When I bring the metal rod closer to these gold foil, that aspect, why does it spread apart? So I want I hopefully will go into breakout rooms. We're just going to take maybe 5 minutes, not 10 minutes because of the time. I really want to go on and share some explanations with you today, so you really have a sense of explanations. So let's just take 5 minutes in breakout rooms and see if you can't draw a model of why those gold leaves spread apart. Now, obviously, I'm expecting you to have some background knowledge because we're all science educators in many respects. So I'm hoping you have this background knowledge. So the goal isn't to be teaching you some new knowledge right now. The goal is to help you understand what a model is and to draw a model that explains this very common phenomena that we always saw that in fact has very important consequences. This idea that charge can transfer, because this is what explains what holds lots of things together. So just take 5 minutes and we'll pop in the breakout rooms and we'll draw some models. Hopefully you can use your whiteboards. Unlike me, I don't know what's going on. I'm going to go play around with my whiteboard as soon as you guys go into your breakout room, see if I can get it to work. And we'll come back in 5 minutes. So it's only going to be a 5-minute session. Maybe 6 minutes, because I want you to draw a model. Hey, Annie. Welcome back, everybody. I'm going to share my screen again. So hopefully you were able to draw somewhat of a model. And I'd like us to share, I'd like one group, maybe two groups, depending how comfortable people feel, to share their models. And the chart I showed you before can actually be used as criteria to actually give feedback to people. So we can provide feedback to people with respect to others who draw models based on the parts of the model, the relationships, and also the relationships between the model and the real world phenomena. So we can use these three criteria. Are all the parts there? Are the relationships there? And does the model really explain the phenomena to give feedback? So with that, I was hoping that'd be one group or two groups that would be comfortable sharing their models. I'll stop sharing, which will allow you to share your model.
I can, if nobody
Okay.
wants.
Go ahead, Darren.
So let's start from some prior knowledge. We know that two charges attract each other if they are, I don't know, in English they called unlike charge, right?
Yeah, it's negative and positive, right? So this
So
would be,
I can call them unlike and like, right?
yeah, call them what? Say it again.
Like and unlike. I heard
Okay,
that.
sure. That's great. Like and unlike.
Is it correct saying like and unlike?
You have like and unlike charges. That's correct.
Yeah, okay. So with different charges and the same charge. So we know that different charges attract each other, and the same or like charges, they repel each other. It doesn't matter two positive charges or two negative charges. So they repel. So when we charge our stick or rod, let's say we charged it positively by some friction, for example. So we just getting close to our, let's say it's system or what. So it means when stick is positive, it will attract electrons. So electrons can flow in a metal. So electrons go up. So it means here we have a lack of electrons. So here more in a leaf, more positive charge stay. So two positive charges repel each other. Let's say about another version. For example, our stick is negatively charged. So if it is negatively charged, it will repel a lot of electrons from the up to down. So all electrons go down. So only positive charge stay here because positive charge protons in a nucleus, so it can't flow. So electrons will be in a leaf. We have extra electrons in leaves. So again, leaves will be charged like likely or with the same charge. So again, it repels. So it doesn't matter how charged our stick, result will be the same. Leaves will repel.
Okay, and any what comments do we have for Darren? Anybody like to comment?
Again, I have a FET to showing charging with by friction. So you see the electric force repels electrons and protons stay because protons inside it's in the nucleus.
You're always moving electrons around. You can never move protons around.
Yeah,
So,
electrons always move.
So what I like
they
about
move,
yeah,
they move up or they move down. That's it.
Yeah, the electrons are moving. That's correct. So what I like about Darren's group's model, and let's talk about the one that's on the right. So first of all, there's the parts are there, right? So he shows both the microscopic parts, the electrons, and he also shows the macroscopic parts. So he shows in the relationships between them. So he shows the negative rod touching the rod of our gadget, and how that then causes electrons to flow down and then causing the leaves to spread apart. And what I like about the leaf part is that he's actually showing the relationship. So because they're negative, they're spread apart, right? So that's the relationship part, which is really important. And Darren, when you were talking, you did also a nice job showing that the electrons were moving down. And if you were just going to do that on a static model, how would you do that? Because right now that's not shown, right? Right now, when I look at this, I mean, when you talked, you did a wonderful job, a very thoughtful job of showing the electrons moving down from the top to the bottom. But you did not, but it's not in the drawing. What would you do to show that in your drawing?
So your question is about how can we show?
Yeah, how can you show the electrons moving from the top down to the leaves? You showed it when you were talking. So how would you
Yeah.
show it just so it's in the picture? What would you show? Yeah, great, right? So now it's complete. So when I looked at the model, when he talked, he showed all of it, but it wasn't in the picture. Now, when I look at it now, we see it in the picture, right? We see all the relationships. We see that the electrons, the negatives, the opposite is moving down, causing the leaves to get a buildup of that negative charge, and then the leaves spread apart. So we now have a much more complete model.
Yeah, and I want to add that this charge is just charge difference, actually.
That's correct.
Yeah, it's very important. It's not. It doesn't mean leaf charged negatively. It doesn't mean it doesn't have a positive charge. So it
That's
has
right.
more negative charge. Just
That's correct. And again, every model has its limitation, because it's hard to show all that. Now, if we had more time, you can make it more elaborate, but models always have some limitations. But on the other hand, we can ask ourselves the question, does this model explain why those leaves spread apart? And if we buy the premise that matter is made up of tiny positive charges and positive charges, negative charges and positive charges, and it's the negative that can flow. If we buy that, then we would agree with this, right? This is a nice model that shows that something that it explains. So nice job. If we go the other way, where the rod was actually positive, then that model also showed a nice example of it as well, right? So if you look at the one on the right, on the left, the positive, because the rod is positive, that causes electrons to flow up to come towards that positive charge, making the leaves more positive than the negative, again, because the positive and positive repel, it spreads apart. So both of these actually do a very nice job of potentially explaining the phenomena. And I had a couple of questions. Let me just check the questions real quick. Right, they're just responding to the questions I asked. So nice job. So if you could stop sharing, I'm going to go back and share my screen. And this is really what, obviously Darren and that group come with a lot of background knowledge. But what we want to do is we want to get our kids to that point, right? This is through instruction. We want to get our students to that point. And so I'm going to share my screen.
and it only 2 years ago.
Yeah, I'm saying it takes time. That's right.
Yeah,
So,
only
so
in my master. Only in my master.
Your master's degree, right? So here's an example of a high school student. This is a 9th grade student who drew this model. So this is a 9th grade student's model. And so now we could look at this and we could say to ourselves, how does this model compare to Darren's model? And you'll notice there's some real close similarities. Both of them had negative charge on the rod. But I'm going to ask you this question. Does this model that's on the screen right now actually do a good of a job of explaining as Darren's model did? And what's missing, right? So if you if you look at Darren's model and you look at this model, what's different between the two models?
There's no mentions of electrons inside the gold leaves, as well as there's non-movements of the electrons.
Right. That's right. So there's no, it's incomplete. The student started, but he didn't show that very important relationship that the electrons will flow down through the metal and flow into the metal leaves and cause them to disperse. So it's an incomplete model. So we would possibly want to give some feedback to the student to say, revise your model to show how the charge rod affects all parts of the electroscope and the foils, because that's what that learner is not doing. So he has the start of a model, but not a complete model. Yes, someone else wrote the same thing in the chat as well. So, and one of the reasons why I really like modeling is this, particularly when I compare it to the one that we saw from Darren's group, this really tells me a lot about the student and his knowledge. He obviously knows something, but he didn't express it completely enough. And so I can work with him by giving this student some really positive feedback, encouraging him to revise his model to say, okay, you showed the negative charges in the rod. Can you show that further about what happens in the entire throughout the electroscope? So it really gives me an image. It provides me to see what that child knows. It's a nice representation of that child's knowledge that allow me to then say something to him, provide that learner with feedback that could really push him forward. So that ends our sort of review of modeling. We're obviously gonna continue with modeling next week, because we're gonna help you learn how to use a tool called Sage Modeler that allows you to do systems modeling. You will notice that the model that Darren drew and this student drew wasn't what the circles with the arrows and the relationships, right? This is more of a mechanistic model trying to show the various parts and how they really impact each other, versus what the circles, how that really that's more of a systems type of model. So next week we're actually going to go more into system dynamic modeling for our time together to next week. But with that, I just want to make sure before we move on to explanations, do you have any questions related to modeling? And again, we are going to be revisiting modeling. We're together through January, I think, and a little bit into February. Many of the curricula that we will be investigating has these modeling aspects to it, and so we will we will revisit ideas related to modeling. But I just want to see, before we move on, does anybody have any questions with respect to modeling? What's going on here? Okay, so I hope you found that little aspect, little segment on modeling valuable. We're going to go on. We're going to talk a little bit more about explanations, and we'll certainly pick this up on Monday again. But just again to restate why it's important is that modeling like explanations is a really important part of science. And not only is, oops, there's a spelling mistake there. Is a really important part of science, but not only is it a really important part of science, it should be a really important part of instruction. Why? Because it can get kids to express their knowledge. It gets kids to be able to talk to one another about that knowledge. And when we get students to express their knowledge and debate what's going on here, what's the best way to show this, or what's the best way to write about it, it can really help them develop their understandings. Project 2061, that many of you probably know, did some analysis of curriculum materials and showed that, previous curriculum materials, nowadays at least in the US, our materials are starting to build explanations and modeling and arguments more into them. Previously, they did not have these important aspects of science in them. And so new materials, and I hope in your own, as you work with your teachers, you will build more explanations and more modeling into your work because they haven't been part of traditional curricula. But, students have difficulty with models explanations. Typically, they don't have problems writing claims. Claims kids can usually do okay, but they have a really hard time specifying the evidence. And I'm pointing this out because I really want you have to focus on this yourself. You're going to have to help your kids understand what's the appropriate evidence that students really need. And most importantly, what they do is they fail to provide the reasoning that would really show why the data that they have supports their claim. They don't put the backing in. They don't put the reasoning in that really shows why that data is actually evidence to support the claim. And the other one you really want to pay attention to is that second bullet under evidence. And this happens too often in our world. People discount data if it contradicts what they believe in. Right? So if there's evidence that's out there, but it's not in their frame, then people just ignore it. And as scientists, we can't do that. We can get rid of data if we find out it's faulty data. If the evidence was, if the experiment was poorly designed, then that's not really strong data. But if there's strong data out there, appropriate data, we have to consider it, even though it contradicts our current thinking. And often what happens is people don't do that. If it supports their position, they accept it. If it doesn't accept if the data doesn't support their position, they ignore it. That is not being a scientist. Right? Scientists look very carefully at the data and they try to say, how does this data really relate to what I know? And how does it really help to explain that phenomena? And as I said the other day, explanations are really critical. If we're really going to get kids to do explanations and modeling, we really got to provide this scaffolding. And we got to also provide opportunities. I don't have that as on the slide, but it's very important. So I'm going to just stress it. We have to provide scaffolds because the scaffolds provide the structure. Eventually, when I want to take those scaffolds away, I don't want to say claim, evidence, and reasoning. I don't want to say, what are your parts of your model? What are the relationships? Those should all fade away as time goes on. But initially, to really get students to be able to build a model, or to construct an explanation, we have to give them that structure: claim, evidence, and reasoning. And then it'll fade away. So that's one critical aspect. The other critical aspect, if we don't provide them, and this is not on the slide, so I'm going to stress it. If we don't, we have to give them opportunities to use that. And it can't just be one. We have to make it part of our instruction, moving from one unit to another unit throughout the year and throughout years. And when we can do that, we'll really help build learners who really have a strong scientific disposition. So we have to initially start off with these scaffolds. We have to provide lots of opportunities. Hopefully in the end, we'll get kids that are really different than children that we've raised in the past, because they'll have more of an understanding of what science is really all about. The other really important aspect behind scaffolding and doing these practices is it really makes scientific thinking strategies explicit to students. So all scientists always look at their data, and they always say to our data, how does this data I have really support my claim? Why is that? How does this data not support my claim? What's going on here, right? So it really pointing out the importance of data, but also having reasoning to say why that data actually supports a claim really brings out, it really makes visible what the scientific enterprise is actually all about. So it really reveals the underlying framework, the tacit knowledge, where tacit means it's not to the forefront. So when we provide these scaffolds, it really brings forward what scientific explanations look like through these scaffolds. So that it's really important to work with your kids initially on to say, what is the structure of an explanation? Help them build that understanding, continue working with them, and then fading that structure away. So as we said, what's a scientific explanation? It's a discussion, it's an argument about how or why a phenomenon occurs and the conditions and consequences of those observed events. And of course, as a result, because of instruction, because we want to help all children, not just the brightest ones in our class, but all children, because science is so important to this day and age, we provide this structure of claims, which is a conclusion of the problem that typically answers a question and relates one variable to another variable. We have to have evidence, that's scientific data that supports the claim, and we need appropriate data. Does that data actually support really an important part of our claim? And is it sufficient? Do I have enough of it? Typically, one piece of data is not enough to support a claim, particularly if it's a high-stake claim. And then reasoning is the justification about why that data counts as evidence to support the claim. And we allow that to happen by using appropriate scientific principles. So again, that's the structure of a scientific explanation that we sort of want to work with our kids to build knowledge of. So here is a very simple example. And it basically shows 4 liquids. It shows, and we know that properties can help identify substances. So we have 4 liquids, and we can see here various properties: density, color, mass, and melting point. And the question is, this is a beginning activity, and you might say in a beginning activity in the structure and properties of matter. Based upon this, we're going to go back in our breakout rooms. We're only going to take 5 minutes, pretty quick. And I want you to write an explanation, claim, evidence, and reasoning about which of these liquids are actually the same substance, and how do you know? Right? You want to make a claim. You want to tell me very explicitly what your evidence is, and what your data is, your evidence, and why that data actually counts as evidence by using scientific principles. So let's go into our breakout rooms. It will just 5 minutes. We're not, again, we don't have, hopefully 5 minutes should be enough time. Let's pop into our breakout rooms, and we'll come back. And then I'm actually going to ask you to share I'm going to ask you to share.
Mr. Burin.
Hi.
Yeah, Mr. Burin,
Yeah.
I haven't
Yes.
got the breakout room for me because I just come from the doctor and then just join Joe's class.
Okay.
Yeah.
Let me see.
Okay, thank you. Yes.
Yep.
Thank you very
Welcome.
much. Yeah.
I think there's someone else on assigned too.
Yeah.
I think there's another person that's not another person not assigned.
Yep. Already assigned them.
I need to go here. Welcome back, everybody. I'm going to share my screen. And okay, so here was our problem. And we went into our breakout rooms. And right now what I'm going to do is I'm going to give you a base rubric. I think everybody can see the base rubric, correct?
Yes.
This is a base rubric. And why do I call it a base rubric? Because we could use it for all explanations. If we wanted to write a more specific rubric, we'd have to tailor it to the particular task. And you can use these base rubrics, this base rubric, to create a rubric tied to a task. But this is just a template that we can use to basically evaluate explanations in general. So when you remember, a rubric gives us criteria and also a level, you might say, of how the kid did, right? So so we have the criteria on the left. It's called the component. I think I like the word criteria better. I'll have to change that. So we've got the criteria on the left, and so you have a claim, a statement that responds to the question asked or the problem posed that relates one variable to another variable. And then we have the level at which kids can do it, right? So you can go from 0 to 2. You can extend it if you wanted to, but at the very least, the student does not make a claim or makes an inaccurate claim. The student makes an accurate claim, but it's incomplete. And then they make an accurate claim and it's complete. Similarly, you can have evidence and the student does not provide evidence or provides inappropriate evidence, which would be a 0. Then you can get a level 1 where the student provides appropriate but insufficient evidence, right? So, and I'll talk about that in the example that we're going to look at in a second, your example. And then they provide both the appropriate and sufficient evidence to support the claim. And the last part is reasoning using scientific principles to show why that data counts. And so as the evidence. And so we see here to begin with, you get 0, there's no reasoning provided. This is very common. And this is what you're really going to have to focus on, that the student has to provide reasoning to really justify why that data is the evidence. It's the hardest part. I get it. You're going to tell me, Joe, this is hard. You're absolutely correct. But this is the one that builds the knowledge. When they can provide, over here on the right side, the row 2, provide reasoning that links the evidence to claim, including appropriate scientific principles. This is the critical one that you have to focus on. The same thing is true when we go to evidence. Often what happens in evidence, you get kids that that provide some of the evidence, but not all the evidence. And once again, you have to push them to provide all the evidence. And sometimes what they want to do is they want to provide inappropriate evidence. So this base rubric really gives us a way of, when we look at an explanation, how to judge it. So what we're going to do, I'm going to sort of modify. I'm not going to actually have us, well, maybe I will. I'm actually going to do it this way. I'm going to show us a couple of explanations to begin with. And then we're going to go look at your explanation. And so this particular explanation is one that that is based upon what you just read. So we'll go back and we'll look at that if we need to look at it. And the student's explanation reads the following. Liquids 1 and 4 are indeed the same substance. Looking at this data, the properties include density, color, and melting point. Mass is not a property. Density, color, and melting point are all the same for liquids 1 and 4. Since all of these properties are the same, 1 and 4 are the same substance. So that's this particular student's explanation. And so what I'd like us to do right now, and the chat says that's a great explanation for a student. Well, let's examine and see if it is a great explanation. Who would like to tell me where the claim is in this particular explanation? Where's the claim?
Liquid 1 and 4 are the same
Yeah,
substance.
the first sentence.
The first
Yeah,
sentence
same
is clean.
Right, really clear, right
Yeah.
here, right?
Yeah.
Does a nice job. Does a really nice job identifying what the claim is. What about the data? Where's the data?
When they mention density, colors, and melting point data, looking at this data is evidence.
Okay, so
The second-
mass, it goes density, color, and melting point are all the same for liquids 1 and 4, right?
Yeah.
That's the data.
Yeah.
He does a nice job of summarizing, he or she does a very nice job of summarizing the data. Where's the reasoning?
Mass is not a property.
Yeah, so since all these are properties, since all these properties are the same, and 1 and 4 are 1 and 4 are the same substances, but he also does a really nice job here of saying, looking at this density, the properties include density, color, and melting point. So that's a key statement, right? So density, color, and melting point are the properties. And since these are all the properties, since all the properties are the same, therefore 1 and 4 are the same. Does a very nice job.
Yeah.
So I really agree with the comment in the chat, Nor, that said this is a great answer for a 7th grade student. It's a fantastic answer for a 7th grade student. So when we look at I have to stop sharing just for a second. I'm gonna start sharing again. So when I look at this comment and I go back for making an accurate and complete claim, I would provide, I would give this person a 2 for evidence, and I would give this person a 2 for the reasoning. A really good, strong example of a scientific explanation. Now here's another one. And so I want us to just take a minute and we can talk about this one as well. Comment here. That's right. The answer for this 2, 2, and 2. So I like this example. Let's score this one now, right? So in the chat, you can sort of provide your score for this, and I'll say what it is. No, the liquids are not the same substance because some are different and some are the same. Like liquid 1 and 4 is just a liquid. It has different mass than liquid 1. Some has different color, like liquid 1 and liquid 2 and liquid 4. They all have no color. But liquid 3, the color is silver, and also liquid 2 and liquid 3 have different density, and liquid 1, 2, liquids 2, 3, and different melting points. So what would we give this kid?
Could you show back the rubric?
Show back the rubric, of course. Okay, so I have one score in the in the chat. So let's just talk about it together. What would we give this kid? So let me ask Peter. Peter, why would you give this person a 0 for claim?
The question was asking whether which of the liquid is the same, and they say, and I guess that's the claim that he says that there's none of the liquids are the same.
Right. So, and so there is this claim, no, the liquids are not the same. And
Also, that's the claim, yeah. So I guess it's 1 0 0.
So so there he has a claim. Well, no, it's an inaccurate claim though, right? So if we look at the rubric,
it's supposed to be 0.
He makes a claim, but it's an inaccurate claim.
Yeah.
So I would give it a 0.
Yeah.
Right. So this is an inaccurate claim. The correct response, as we saw in the previous one, is that liquids 1 and 4 are the same. This person says none of them are the same. So it's an inaccurate, an incomplete, it's an inaccurate claim. So I would give him a 0. What about for evidence? Ari, what would you say about, you gave him a 1. Why 1?
For his so-called claim, he actually give evidence that basically support his answers, but of course there are other things that are not related given. So liquid 1 and they are the same, different mass, but basically, yeah. So by then the students provide whatever evidence that he or she could put in, and just like, that's why I'm giving 1, because evidence is still there, but the evidence is not accurate, or the evidence might not support the claim properly.
Right. So I liked your response there. As teachers, we're going to have to make this decision all the time on ourselves, right? In this particular case, the student made a wrong claim, but then he did provide evidence to support his claim, right? So he was he said none of the liquids are the same, and then he went about and tried to show how the data actually supports his claim. Of course, it's inaccurate, but I would probably give him a 1, like Ari said, simply because, I want to give the kid some credit. What about evidence? I'm sorry, what about reasoning? Is there any reasoning here?
I think that
Again,
no reasoning found in the explanation.
Right. I probably would give the student a 0 for reasoning. I kind of rewarded him a little bit by giving him a 1 for evidence, but there's no reasoning where he basically gives me the correct scientific idea that properties can identify substances. And that's what the kid doesn't know, right? The kid, when I read the student's response, he doesn't understand that properties of substances can identify them. And that's so I would probably give this student a 0 when it comes to from a reasoning standpoint, because that's the important part of this particular task. So when we look at the task again, right? So he's reading the data table, but he doesn't understand what identifies one substance from another substance. So I would give him a 0 when it comes to reasoning. So my score for this child would be a 0, 1, 0. Okay, so now we're going to go to another quick item. This is a much more challenging item. And it says here, but again, it builds off this idea of properties. So this one says Carlos takes some measurements of 2 liquids, butanic acid and butanol. Then he stirs the 2 liquids together and heats them. And after stirring and heating the liquids, they form two separate layers, layer A and layer B. And Carlos uses an eyedropper to get a sample from each layer and take some measurements of each sample. And here is his data, right? So we see that butanic acid and butanol have different densities. They have different melting points. He started with a different amount of mass, and they have different volumes, and they have different solubility in water, and they have the same solubility in water. Afterwards, we see that the density of layer A and layer B are different from each other. We see that the melting point and are different from the two things, and we see that the masses have changed, the volume has changed, and the solubility in water has changed. So the question becomes, did a chemical reaction occur? And so that's what we want to write our explanation on. Did a chemical reaction occur? Now, we're not going to go in the breakout rooms because we don't have enough time. So I just want you to think about it to yourself. And then we're going to look at one example, and we're going to analyze that one example. So just take a minute and say, what would be your claim? Did a chemical reaction occur? What's the evidence that a chemical reaction occurred? And what would be the reasoning that a chemical reaction occurred? So we'll just take a minute, think to yourself what your explanation would be in this particular case. And then we'll go look at an example. Again, my goal is not to teach you the science today. My goal is to teach you the structure of an explanation. You could jot a couple notes down for yourself so you know what your explanation is. Okay. So we're going to go look at an example. And see and give it a score. So here is an example that one student wrote. He said, yes, there was a chemical reaction because the density changed, the melting point changed, and the mass and volume, the solubility, all of them really changed. If there wasn't any chemical reaction, then the data table would be the same. So this is a really nice example to explore for a variety a reason. Nor in the chat put down the claim is correct, right? And you're right, the claim is correct. If we go back to our rubric, right? He makes an accurate claim. Right, but I would argue it's incomplete. I would give him a 1. And the reason why is because he just says, yes, there was a chemical reaction. And one of my goals as challenge is to get kids to really express their thoughts deeply. And in this case, I would want the kid to say, yes, a chemical reaction occurred, because when I reacted butanic acid with butanol, I formed 2 different substances. That would be a more accurate claim. Yes, a chemical reaction occurred because mixing butanol and butanic acid resulted in 2 new things. So yes, I'd give him a 1. Now, what about his evidence? What would you tell me about his evidence? And again, I'm going to use Nora. I hope you don't mind this. I'm going to use you wrote it in the chat, so I'm going to use your example. Because new substances are formed as different physical properties. And so he says, yeah, okay. So we do see, when we look at this example, we do see that things changed. But not all of these count. So he gave some of the data that was accurate. The density changed, right? So none of the density between layer 1 and layer B, they're different, but they're also different from butanic acid and butanol. And that's a good piece of evidence, data, to show that, hey, a chemical reaction occurred. But just by saying density, that would be insufficient. But now I go to volume, I go to melting point. And I also notice, hey, the melting points are different. Butanic acid, what formed has very different melting points than what was the original substance. So again, I have more evidence to support my claim that in fact a chemical reaction occurred. But now I go to mass. And he also said that the mass changed, right? So mass and volume also changed. But mass and volume are not properties of substances. They're properties of a sample, right? Every sample has a mass, but it's not a characteristic property. It doesn't help me identify the substance. So while he gave some appropriate data, he also gave some inappropriate data. So in this case, from looking at the rubric, I would only give this child a 1 when it comes to evidence, right? Provides appropriate but inefficient data to support his claim, and also may include, so he provided appropriate and he also provided sufficient, but he included some inappropriate data. So I would have to give this student a 1 and not a 2. Similarly with his reasoning, and again, this one's going to be a little bit debatable, because with his reasoning, he doesn't really say, he says, this is his reasoning, if there wasn't any chemical reaction, then the data table would be the same. That's a true statement. And the data table did change, particularly with data and data melting point and solubility, but it's incomplete, because the real data, the real evidence, the real reasoning that I would be looking here for is that when a chemical reaction occurs, the new substances have different properties than the reactants. And we know that properties identify substances. That's how I know a chemical reaction occurred. So I would say in this particular case, his reasoning is incomplete and insufficient. And I would be borderline as a teacher. Is it 0 or is it 1? I don't really, it's questionable. It's not necessarily a very solid response. So I think I would agree with Nora. I would probably give him a 0, because I really want to put, especially in, I like to use these kind of questions as formative. So I'd want to push this kid's thinking to really make his thinking much deeper and much richer than it is. Here's another one, and we'll just do this one really quick because we're running out of time. A chemical reaction did occur. Again, a claim, but it's incomplete. So I'd probably give it a 1. The evidences of this is that neither of the beginning substances share the same amount of density with either the end substances. Also, the melting points change from 7.9 to 8.9. So he gives data. Another piece of evidence is the mass change. That's inappropriate. So the mass has nothing to do with did a chemical reaction occur, because maybe a gas formed, right? So the masses can change for a variety of different reasons. So I would not, again, I would not give him a complete response here. Because the mass and volume decreased so much, I think that a gas form, that's good. So he's got a reason for why that changed. The data is evidence of a chemical reaction. Again, this is another example of insufficient reasoning. And so you can look at that a little bit longer after we take off. But again, I would probably score this one a 1-1-0. I'll skip that. This is actually a really nice, this happened to me several years ago. I went to the museum in New York City, the Natural Science Museum, and they had a wonderful example of an explanation, right? So they're trying to explain what happened to the dinosaur. And so just, afterwards, you might want to just take a second and read through this, because it really does give a really nice, what killed the dinosaurs, right? So it starts off, I typed it off so you could see all of it. So what killed the non-avian dinosaurs a long time ago? And it says there's abundant, and it then goes about giving you evidence and a claim, evidence, and an explanation. So it's actually quite a nice little example to look at. Anyways, I want to just wrap up because we're running out of time to see if you have any last minute questions. We really, curriculum materials can really support teachers in doing these various scientific practices. But if we really want to make them meaningful for children, we really have to, we have to express what's going on. So we have to tell them, science is all about writing explanations. And that's what we're doing in our class. We're going to actually write an explanation. And so by writing an explanation and telling them what are the parts of an explanation, we can really push their thinking forward. We also want to be able to, so that's discussing the rationale, right? Scientists engage in writing explanations. Scientists engage in constructing scientific models. That's why we're doing this in a class. We want to make the framework explicit. So in the case of explanations, it's claim, evidence, and reasoning. In the case of modeling, it's specifying the parts, the relationships, and do those relationships actually explain the phenomena? As classroom teachers, I'm using the term model now in a different way. We actually want to demonstrate. Maybe I should change that to demonstrate. Let's change that to the better term there is actually demonstrate. Can you still can you see my screen still? I hope yes. Maybe not.
No.
No.
Yeah, let me go back. Here we go. So I'm going to change this. Now you can see it, right? I'm going to change this modeling to demonstrate because I don't want to give people constraint. We want to demonstrate the use of the practice. We also kind of want to pull on their everyday experiences. It really helps build knowledge. And we want to provide these opportunities to use these scientific practices. So if you really want to get children good at this building models and building explanations, we have to make the rationale explicit, right? We want to tell them why scientists do this practice. We want to make the framework that we're using explicit. We want to demonstrate how to do it, and we want to provide them opportunities how to do it. And if we can do that, then we're going to actually really support our children in using these very complex practices. So I know the last couple of days, some of you found these very challenging. They should be. These are not things that we do every day or we've done in science instruction. So that you found them challenging is I totally understand that. But if we provide opportunities, then hopefully it becomes more transparent. And my goal is that by the end of the time we're together, you're going to be really good at writing. You're going to really know what explanations are, and you're really going to know what modelings are, and you're going to really be able to explain that to other people. All the curriculum that you will experience have all these embedded, and you'll be using them over and over and over again, and you'll see 3 different examples of curriculum that actually show how you do that. So that's my goal, that's my hope. It's getting late, but if someone has a question, I'm more than happy to try to respond to it. Anyway, thank you, Peter. It's late on Friday night. I want to really thank you guys for being here. It really shows your dedication and your sincerity to want to improve science education in your country, because science education is just so important. And so thank you for staying with me so late at night. I appreciate your efforts. I'll see you once again on Monday evening, bright and early on my Monday morning, but and on your evening on Monday. So have a very pleasant weekend. And if you have questions, I'll tell Ann to start off Mondays. Ann is on with water quality again on Monday, but I'll ask her to start off to see if you have any general questions about modeling and explanation. The one question I wanted to ask you, would it help you if I provided you with some simple readings related to modeling and explanations? I could find some pretty easily. Would that be valuable to give you some short readings? Okay, Nor gave me a heart. Okay, that's a hands up. I
Yes,
see.
please.
Norma.
Yes,
What were you
please, Joe.
Okay, I will try to find some readings, and I'll share them with Buren over the weekend, and we'll put them in wherever you pick up the PowerPoints. We'll have them in the same place. I'm not sure if Buren is sharing the Google folder with you.
Yeah.
So I'll put them in the Google folder. I'll call them readings on explanations and modeling, and you can go and you can find them. I'll try to do that during the day today. Anyways, I'm late for another meeting because it's my beginning of my day. So I have to continue with my next meeting with some colleagues. So have a good weekend. Thank you once again, and I'll see you your Monday evening and my Monday morning. Bye-bye.
Bye-bye.
Bye.
Thank
Thank you,
Bye-bye.
Joe.
Thank you.
Bye-bye,
Thank you.
everyone.
Bye-bye.
Bye-bye.
Bye.
A great weekend.
Bye. Have a good weekend.
Have a good weekend, everybody.
Yeah.
Thank you.
Happy
You too.
weekend.